According to the National Electrical Code, tin copper cannot be used as a concrete encased electrode. The NEC specifies that a concrete encased electrode must be made of bare copper conductor, and the code states that the conductor should not be smaller than 4 American wire gauge. The use of any coating, including tin plating, is not permitted for concrete encased electrodes. There are several reasons why tin copper cannot be used as a concrete encased electrode. Firstly, reduced conductivity is a factor. Tin plating reduces the electrical conductivity of copper. This reduction increases the resistance of the concrete encased electrode. The higher resistance can compromise the effectiveness of the concrete encased electrode in dissipating electrical fault currents. Secondly, there is the issue of reduced corrosion resistance. Tin plating can provide some corrosion protection to copper, but the protection is not as effective as the natural patina that forms on bare copper when exposed to moisture and air. Over time, the tin plating can wear off or corrode. This wearing away exposes the underlying copper to corrosion. Thirdly, bonding difficulties arise from using tin copper. Tin plating can interfere with the bonding of the concrete encased electrode to other grounding conductors. The tin plating creates a barrier that prevents the formation of a good electrical connection. Now let's address exceptions for ground rings. The NEC prohibits the use of tinned copper for concrete encased electrodes, but it does not specifically mention ground rings. In some cases, engineers may specify tinned copper for ground rings due to its enhanced corrosion resistance and ease of welding. However, it is important to note that this is not necessarily a code-compliant application. In conclusion, the use of tinned copper for concrete encased electrodes is prohibited by the NEC. Using tinned copper for this purpose can compromise the safety and effectiveness of the grounding system. It is critical to adhere to the NEC requirements to ensure proper grounding and electrical safety. The NEC Section 250.52 A3 details the requirements for concrete encased electrodes, emphasizing the use of bare or zinc galvanized or other electrically conductive coated steel reinforcing bars or rods, or bare copper conductor. The key requirement is to ensure a reliable, low-impedance connection to the earth. When selecting grounding electrodes, it is important to consider factors such as soil conditions, corrosion potential, and local electrical codes. For example, in areas with highly corrosive soils, additional measures may be necessary to protect the grounding electrode from corrosion. These measures may include using corrosion-resistant materials or applying protective coatings. Ultimately, the goal is to provide a safe and effective grounding system that protects people and equipment from electrical hazards. Adhering to the NEC guidelines is the most important aspect when it comes to ensuring electrical safety in these systems. For example, NEC Section 250.66 provides guidance on sizing grounding electrode conductors. This section outlines the requirements for the size of the conductor that connects the grounding electrode to the electrical system. The size of the grounding electrode conductor is based on the size of the service entrance conductors. Additionally, NEC Section 250.68 addresses the requirements for connecting grounding electrodes. This section specifies how the grounding electrode conductor should be connected to the grounding electrode. The connection must be made using listed connectors or other approved means. In addition to the specific requirements for concrete encased electrodes, the NEC also provides general requirements for grounding and bonding. These requirements are found in Article 250 of the NEC. Article 250 covers topics such as grounding system design, grounding electrode systems, and equipment grounding. Grounding electrode systems are essential for providing a low-impedance path for fault currents to return to the source. This helps to ensure that overcurrent protective devices, such as circuit breakers and fuses, operate properly to clear faults quickly and safely. The grounding electrode system typically consists of one or more grounding electrodes that are connected to the electrical system. Common types of grounding electrodes include ground rods, ground plates, and concrete encased electrodes. In addition to grounding electrodes, bonding is also an important aspect of electrical safety. Bonding involves connecting all metal parts of an electrical system together to create a common ground potential. This helps to prevent voltage differences from developing between different metal parts, which could pose a shock hazard. The NEC provides detailed requirements for bonding in Article 250. These requirements cover topics such as bonding of metal water pipes, bonding of metal gas pipes, and bonding of metal equipment enclosures. Properly implemented grounding and bonding systems are crucial for ensuring the safety of electrical systems. These systems help to protect people and equipment from electrical hazards by providing a low impedance path for fault currents and by preventing voltage differences from developing between different metal parts. The NEC provides comprehensive guidelines for grounding and bonding, and it is essential to follow these guidelines carefully to ensure the safety of electrical systems. Now consider the implications of using dissimilar metals in grounding systems. When dissimilar metals come into contact in the presence of an electrolyte, such as moisture, galvanic corrosion can occur. This type of corrosion can degrade the metal components of the grounding system, leading to increased resistance and reduced effectiveness. To prevent galvanic corrosion, it is important to select compatible metals for grounding system components. For example, copper grounding conductors should be connected to copper grounding electrodes, and aluminum grounding conductors should be connected to aluminum grounding electrodes. If it is necessary to connect dissimilar metals, a suitable transition fitting or connector should be used to prevent direct contact between the metals. Furthermore, regular inspection and maintenance of grounding systems are essential for ensuring their continued effectiveness. Grounding electrodes should be inspected periodically for signs of corrosion or damage. Grounding conductors and connections should be checked for tightness and proper installation. Any damaged or corroded components should be replaced promptly to maintain the integrity of the grounding system. In addition to the NEC requirements, local electrical codes and regulations may also apply to grounding systems. It is important to consult with local authorities to determine the specific requirements for grounding systems in a particular area. These requirements may vary depending on factors such as soil conditions, climate, and the type of electrical system being installed. When designing and installing grounding systems, it is also important to consider the potential for lightning strikes. Lightning strikes can introduce large amounts of energy into the electrical system, which can damage equipment and pose a safety hazard. To protect against lightning strikes, lightning protection systems can be installed. These systems typically consist of lightning rods, grounding conductors, and surge protective devices. The lightning rods intercept lightning strikes and provide a path for the energy to flow to ground. The grounding conductors carry the energy to the grounding electrode system, and the surge protective devices protect sensitive electronic equipment from damage. The NEC provides guidelines for lightning protection systems in Article 250. These guidelines cover topics such as the location of lightning rods, the size of grounding conductors, and the selection of surge protective devices. Properly installed lightning protection systems can significantly reduce the risk of damage and injury from lightning strikes. The performance of a grounding system can be evaluated by measuring its impedance. Ground impedance is a measure of the opposition to the flow of alternating current in the grounding system. A low ground impedance is desirable because it indicates that the grounding system is effective at dissipating fault current. Ground impedance can be measured using a ground impedance tester. This device injects a small amount of current into the grounding system and measures the resulting voltage drop. The ground impedance is then calculated using Ohm's law. The measured ground impedance should be compared to the allowable limits specified in the NEC or local electrical codes. If the ground impedance exceeds the allowable limits, corrective action should be taken to improve the grounding system. This may involve adding additional grounding electrodes, improving the connections between grounding conductors, or replacing corroded components. The location of grounding electrodes is also an important consideration. Grounding electrodes should be located in areas where the soil is moist and conductive. This helps to ensure that the grounding electrode is effective at dissipating fault currents. Grounding electrodes should also be located away from underground utilities, such as gas pipes and water pipes, to prevent damage to these utilities. The NEC provides guidelines for the location of grounding electrodes in Article 250. These guidelines cover topics such as the minimum distance between grounding electrodes and the depth at which grounding electrodes must be buried. In addition to the physical components of the grounding system, the quality of the installation is also critical. Grounding conductors must be properly sized and installed to ensure that they can carry the expected fault currents. Connections between grounding conductors must be tight and corrosion resistant. Grounding electrodes must be properly driven into the ground and securely connected to the grounding conductors. A thorough inspection of the grounding system should be performed after installation to verify that all components are properly installed and connected. This inspection should include a visual inspection of all grounding conductors and connections, as well as a measurement of the ground impedance. Any deficiencies that are identified during the inspection should be corrected promptly. In conclusion, grounding systems are essential for electrical safety. They provide a low impedance path for fault currents to return to the source, helping to ensure that overcurrent protective devices operate properly to clear faults quickly and safely. The NEC provides comprehensive guidelines for grounding and bonding, and it is essential to follow these guidelines carefully to ensure the safety of electrical systems. Regular inspection and maintenance of grounding systems are also important for ensuring their continued effectiveness. By following these best practices, it is possible to create safe and reliable electrical systems that protect people and equipment from electrical hazards. Let's shift the focus now to specific scenarios where grounding is critically important, such as in healthcare facilities. Healthcare facilities contain a wide array of sensitive electronic equipment that is vital for patient care. These facilities also have a higher concentration of electrical equipment in close proximity to patients and medical staff. As a result, proper grounding is especially critical in healthcare facilities to protect against electrical shock hazards and to ensure the reliable operation of medical equipment. The NEC provides specific requirements for grounding in healthcare facilities in Article 517. These requirements cover topics such as isolated power systems, patient equipment grounding, and the grounding of sensitive electronic equipment. Isolated power systems are used in operating rooms and other critical care areas to provide an extra layer of protection against electrical shock hazards. These systems use a special transformer to isolate the electrical power from the main electrical system. This isolation helps to prevent leakage currents from flowing through the patient, which could cause electrical shock. Patient equipment grounding is another important aspect of grounding in healthcare facilities. All patient-connected equipment must be properly grounded to prevent electrical shock hazards. This includes equipment such as electrocardiographs, electrosurgical units, and infusion pumps. The grounding conductors for patient equipment must be sized and installed according to the NEC requirements. The grounding of sensitive electronic equipment is also critical in healthcare facilities. Sensitive electronic equipment, such as MRI scanners and CT scanners, can be susceptible to electrical noise and interference. Proper grounding can help to minimize electrical noise and interference, ensuring the reliable operation of these devices. In addition to the NEC requirements, healthcare facilities may also have their own specific grounding requirements. These requirements may be based on recommendations from organizations such as the National Fire Protection Association (NFPA) and the Joint Commission. It is important to consult with the facility's engineering staff and safety officers to determine the specific grounding requirements for a particular healthcare facility. Regular testing and maintenance of grounding systems are also essential in healthcare facilities. Grounding systems should be tested periodically to verify that they are functioning properly. This testing should include measurements of ground impedance and leakage current. Any deficiencies that are identified during the testing should be corrected promptly. Healthcare facilities should also have a comprehensive grounding maintenance program in place. This program should include regular inspections of grounding conductors, connections, and equipment. The program should also include procedures for addressing any grounding problems that are identified. By following these best practices, healthcare facilities can ensure that the grounding systems are functioning properly and that they are providing a safe and reliable electrical environment for patients, medical staff, and visitors. Now, let's consider the role of surge protective devices, or SPDs, in a comprehensive grounding system. While a well-designed and installed grounding system is essential for protecting against electrical faults, it may not be sufficient to protect against transient voltage surges, such as those caused by lightning strikes or switching events. Surge protective devices are designed to protect electronic equipment from these transient voltage surges. SPD work by diverting the surge current to ground, preventing it from reaching the protected equipment. SPD are typically installed at the service entrance of a building, as well as at branch circuit panels and individual equipment locations. The NEC provides requirements for SPD in Article 285. These requirements cover topics such as the selection, installation, and wiring of SPD. When selecting SPD, it is important to consider the voltage rating, surge current capacity, and protection mode. The voltage rating should be appropriate for the voltage of the electrical system. The surge current capacity should be sufficient to handle the expected surge currents. The protection mode indicates the type of surges that the SPD is designed to protect against. SPD are available in a variety of protection modes, including line to ground, line to neutral, and line to line. The installation of SPD is also critical. SPD should be installed as close as possible to the equipment that they are protecting. The wiring should be kept as short and straight as possible to minimize impedance. SPD should also be properly grounded to ensure that they can effectively divert surge currents to ground. Regular testing and maintenance of SPD are also important. SPD should be tested periodically to verify that they are functioning properly. This testing can be performed using a surge tester. Any SPD that fail the testing should be replaced promptly. It's also important to maintain a record of SPD installations, testing, and maintenance. This record should include the date of installation, the results of any testing, and any maintenance that was performed. By following these best practices, it is possible to create a comprehensive grounding and surge protection system that protects electronic equipment from both electrical faults and transient voltage surges. In addition to the technical aspects of grounding and surge protection, it is also important to consider the regulatory and compliance requirements. Electrical installations are subject to a variety of regulations and codes, including the NEC local electrical codes and industry standards. Compliance with these regulations and codes is essential for ensuring the safety of electrical systems and for avoiding potential penalties. The NEC is the most widely adopted electrical code in the United States. It is published by the National Fire Protection Association (NFPA) and is updated every 3 years. The NEC provides comprehensive requirements for electrical installations, including grounding and bonding. Local electrical codes may also apply to electrical installations. These codes may be adopted by state, county, or city governments. Local electrical codes may be based on the NEC, but they may also include additional requirements that are specific to the local area. Industry standards may also apply to electrical installations. These standards may be developed by organizations such as the Institute of Electrical and Electronics Engineers (IEE) and Underwriters Laboratories (UL). Industry standards may provide more detailed guidance on specific aspects of electrical installations, such as grounding and surge protection. Compliance with these regulations and codes is essential for ensuring the safety of electrical systems. It is also important to stay up to date with the latest changes to these regulations and codes. Electrical contractors should have a thorough understanding of the applicable regulations and codes and should ensure that their work is in compliance with these requirements. Electrical inspectors are responsible for verifying that electrical installations are in compliance with the applicable regulations and codes. Electrical inspectors may perform inspections at various stages of the installation process, including the rough-in stage and the final inspection stage. Electrical inspections help to ensure that electrical installations are safe and compliant with the applicable regulations and codes. In conclusion, grounding is a critical aspect of electrical safety. By following the requirements of the NEC local electrical codes and industry standards, it is possible to create safe and reliable electrical systems that protect people and equipment from electrical hazards. Regular inspection and maintenance of grounding systems are also essential for ensuring their continued effectiveness. By following these best practices, it is possible to create a comprehensive grounding and surge protection system that protects electronic equipment from both electrical faults and transient voltage surges. Finally, let's underscore the importance of continuous learning and professional development in the field of electrical engineering and electrical safety. The electrical industry is constantly evolving, with new technologies, materials, and codes being introduced regularly. Staying abreast of these changes is essential for electrical engineers and electricians to maintain their competence and to ensure that they are providing the safest and most reliable electrical installations possible. There are many resources available for electrical engineers and electricians to continue their education and professional development. These resources include courses, seminars, conferences, and publications. Courses and seminars are offered by a variety of organizations, including universities, colleges, trade schools, and professional associations. These courses and seminars can cover a wide range of topics, from basic electrical theory to advanced grounding and bonding techniques. Conferences are another great way to stay up to date with the latest developments in the electrical industry. Conferences typically feature presentations by leading experts in the field, as well as opportunities to network with other professionals. Publications are also a valuable source of information for electrical engineers and electricians. There are many trade magazines, journals, and websites that cover the electrical industry. These publications can provide information on new technologies, code changes, and best practices. Professional certifications are another way to demonstrate competence in the electrical field. There are a variety of professional certifications available, such as the Professional Engineer P license and the Certified Electrical Safety Compliance Professional CESP certification. Professional certifications can enhance career opportunities and demonstrate a commitment to professionalism. Continuing education units, or CEUs, are often required to maintain professional licenses and certifications. CEU can be earned by attending courses, seminars, conferences, and other educational activities. It is important to track CEU carefully and to ensure that all requirements are met. Mentorship is another valuable way to learn and grow in the electrical field. Experienced electrical engineers and electricians can provide guidance and support to those who are new to the profession. Mentorship can help new professionals to develop their skills, build their confidence, and advance their careers. Participating in professional organizations is another way to stay connected to the electrical industry. There are many professional organizations for electrical engineers and electricians, such as the Institute of Electrical and Electronics Engineers IEE and the International Association of Electrical Inspectors IE. These organizations provide opportunities for networking, professional development, and advocacy. In conclusion, continuous learning and professional development are essential for electrical engineers and electricians to maintain their competence and to ensure that they are providing the safest and most reliable electrical installations possible. By taking advantage of the many resources available, electrical professionals can stay up to date with the latest developments in the industry and can advance their careers.